Scientists have just uncovered a groundbreaking discovery in quantum physics: Parap particles, a brand new type of particle that challenges everything we know about the universe's building blocks. Unlike bosons and fermions, the two categories we've relied on for decades, Parap particles introduce a whole new way of thinking about matter and energy. This discovery could revolutionize quantum computing, secure communication, and even material science. In this video, we'll explore what Parap particles are, why they're so important, and how they could reshape the future. For over a century, quantum physics has told us that particles fall into two categories: bosons and fermions. Think of bosons like the life of the party. They can share the same space, hanging out in groups. Photons, which make up light, are bosons. Then there are fermions, the introverts of the quantum world. They follow strict rules like the Pauli exclusion principle, which says two fermions can't occupy the same state. This principle is why atoms form the way they do and why you don't fall through your chair when you sit down. But now, researchers from Rice University have thrown a wrench into this tidy framework. Caden Hazard and Gan Wang published a study in Nature showing that a third category of particles might exist: Parap particles. These aren't bosons and they aren't fermions, they're something entirely different. Using advanced mathematics, the researchers found that Parap particles can emerge in certain systems and defy the traditional rules we thought governed all particles. So why is this so important? For starters, if Parap particles are real, they don't just add a new type of particle to the mix, they challenge the fundamental way we classify matter. This could rewrite what we know about quantum mechanics, opening the door to discoveries we can't even imagine yet. Let's get into how this works. The idea of Parap particles isn't brand new, it's been around since the 1950s. Back then, scientists theorized that particles beyond bosons and fermions might exist, but as the years passed, they concluded that these so-called Parap particles were really just bosons or fermions wearing a different disguise. That is, until now. Hazard and Wang revisited the concept using cutting-edge mathematical tools. They relied on something called the Yang-Baxter equation, which helps describe how particles behave when they swap places. They also used Lie algebra and tensor network diagrams, fancy tools for understanding symmetry and quantum states. What they found was groundbreaking. Under the right conditions, particles could behave in ways that don't fit into the boson or fermion categories. These are the Parap particles. Here's where it gets really intriguing. Parap particles don't just exist in the traditional sense, they emerge as excitations in materials like vibrations or magnetic ripples. Imagine you're looking at a calm lake and suddenly ripples appear out of nowhere. Those ripples aren't solid objects, but they're real, and follow their own rules. They emerge in condensed matter systems like magnets and exhibit behaviors that challenge everything we know. Even more interesting, these particles behave in strange ways when they interact. When they swap places, their internal states change. This is completely different from what bosons and fermions do. It's like playing a game where the pieces transform every time you move them. Now that we know what Parap particles are, let's talk about why they matter. One of the most exciting possibilities lies in quantum computing. Right now, quantum computers use qubits to process information. Qubits are incredibly powerful but also delicate. They're prone to errors from environmental disturbances. Parap particles, with their unique properties, could lead to more stable qubits capable of resisting these disturbances. This means faster, more reliable quantum computers solving problems that today's computers cannot, like unraveling protein folding in medicine, optimizing supply chains globally, or revolutionizing cryptography. But it doesn't stop there. These particles could also revolutionize secure communication. Their ability to change internal states during exchanges could allow for entirely new ways to encode information. Imagine sending a message that's completely immune to hackers because it's encoded in a way no one can crack. This innovation could transform cybersecurity, protecting sensitive information like financial data or national security communications in ways we've never seen before. Beyond computing, Parap particles have profound implications for material science. Their unique behaviors could inspire materials with unprecedented properties, like superconductors operating at room temperature or magnets with ultra-high efficiencies. Such advancements could drive transformations in energy storage, transportation, and even space exploration technologies. Interestingly, the discovery of Parap particles draws parallels with anyons, another exotic particle. Anyons, discovered in two-dimensional systems, challenge conventional particle classification by introducing fractional quantum states. These particles have already demonstrated immense potential in topological quantum computing, where their braided states allow for fault-tolerant and robust qubits. The leap from anyons to Parap particles expands these possibilities, as Parap particles extend the concept to three-dimensional systems, unlocking a wider array of applications in quantum systems and condensed matter physics. What's more, Parap particles could redefine our understanding of particle interactions in quantum entanglement. This ties into another major quantum discovery, the quantum spin liquid state, a rare state of matter where entangled particles exhibit highly unusual magnetic properties. These discoveries collectively push the boundaries of what we know about particle behavior in complex systems. Of course, we're still in the early stages. Right now, these particles are a theoretical concept, and proving their existence experimentally will be a challenge. Scientists will need to design experiments using materials where these are likely to emerge. This could involve manipulating quantum systems at incredibly small scales, which is no small feat. But with advances in nanotechnology and quantum research, it's only a matter of time before we see these particles in action. The particles also force us to rethink what we know about matter, energy, and the rules that govern them. Every time we expand our understanding of the quantum world, we take another step toward answering some of the universe's biggest mysteries. Thank you so much for watching. If you enjoyed this video, don't forget to like, share, and subscribe for more exciting updates on the latest in science and technology. Stay curious and see you next time.